welcome you all in this NPTEL online certification course on mechatronics. Today we are going to talk about the dynamic response of system. In last three lectures, we have studied the modeling for mechanical system, electrical system, hydraulic and pneumatic system. Okay. Now, in this lecture I would like to explain the dynamic response of the system and what are the various response measuring parameters which I am going to discuss at the end of towards the end of this lecture. So, most important function of a model is to predict what output be there for a particular type of input. So, the models which we have developed in last three lectures. Okay. So, the purpose of those models is to predict the output for a particular input. Okay. Now, here we are concerned about what happens at a static situation, okay, that is when steady state is reached, or how output changes with time when there is change in input, okay, or how output changes with time when there is change in input itself with time. Okay. So, these are the various concerns. Various system output or input can be both a function of time, and we have seen that the differential equations are used to depict the relationship between the input and output, whether it is a first order system or it is a second order system. Okay. So, we see that say function dx by dt represents basically the first order system, and d square x by dt square represents the second order system. Now, let us see the example of a first order system. So, as I explained you in the last lecture, suppose there is a tank and there is a water filled up to a height h, and pressure at the top and bottom are say P1 and P2, and there is a say a valve through which the discharge takes place, okay, and as say P2 is the pressure here after the valve. Okay. So, we can write the expression for this as we have derived in the previous lecture. Okay. We can write the expression for flow through the valve, and the equation will be P1 minus P2 is equal to RQ, okay, and this can be written in this particular form. So, this is our first order differential equation. Here what you can see is that we are getting expression in terms of height h of the water in the tank, okay, and it is a natural response. So, there is no forcing function here. Okay. So, we have the right hand side is equal to 0. If I talk about force response, so force response can be considered if we consider here that the flow is taking place with the help of there is some input over here, say Q1, and rest of the things are same. Okay. So, again we can as we have seen in the last lecture using the equation for the capacitor as well as the expression for the resistance through the valve, we can derive the equation like this. Okay. And here again you can see that we have the equation basically depicts the variation of h with time, and in the right hand side we have Q1 which is nothing but the input to the tank over here. So, this system equation has got a forcing function. Okay. Now, the total response of any system is basically consist of the transient response as well as the steady state response. Okay. Transient response is the one which change, it occurs when there is change in the input to the system and it dies away quickly, and the steady state response actually remains, that is the response which remains after the transients have died out. So, to give the example of transient and steady state response, we can just consider as a spring and say there is a hanger at the end of the spring, and if I add a certain weight to that hanger, then the spring will be getting displaced. Okay. So, this is how the displacement of the spring, if I plot with time. Okay. So, this is how it is going to be. So, this is basically our the transient response, and this part is the steady state response. Okay. So, this is what I mean by the transient and steady state response. Now, the input various types of input can be used to excite the system. So, it could be a step input, okay, or it could be impulse input, or it could be a ramp input, or the input could be a sinusoidal input. Okay. So, say ramp input is defined as y is equal to k t, sinusoidal we can define as y is equal to k sin omega t, and similarly this impulse at some time, and step is having a certain value, okay, at time t greater than 0. Okay. So, this way these are the various types of inputs. Okay. Now, let us take the example of a first order system. Okay. So, first order system, suppose I have got a system, there is some input say y t and there is some output x t. So, what we are interested in seeing that for a given type of input, what my output varies, how my output varies. Okay. So, this is the form of the expression for the first order system, which we have just seen over here. Okay. So, this is what we have seen. So, this is the example of the first order system. Okay. So, this is what we have seen. Okay. So, this is there. Now, if I talk about the natural response of the first order system, so naturally I make the forcing function 0 here if I want to have the natural response. Okay. And it is a first order differential equation basically. So, its solution could be of the form x is equal to a e to the power s t, where a and s are constants. Okay. And this, if we substitute it over here, then we substitute, if this solution over here, we can get the value of s as this one. Now, if I substitute the value of s, this is the solution of the equation which I get. Here there is a initial a constant which can be evaluated by the initial condition. So, suppose at time t is equal to 0, there is some output. Okay. So, if I put that in this at t is equal to 0, if I put x is equal to 1, say, so I will get a is equal to 1 from here. So, this is the solution for the expression. So, this is actually what I said as the natural response. Okay. So, this is the natural response for the first order system. Now, let us see the response of first order system with forcing function. So, suppose I have got a forcing function here B0 y, okay, where y is the input and B0 is some constant. So, its a solution, let us assume that the solution has got a transient part say u and steady state part v. Okay. So, I can assume the solution of this form, I can substitute the solution in this expression, okay, and then I can simplify it. So, I get this form. Okay. So, if I assume say this part is equal to 0, then naturally this part happens to be equal to 1. Okay. So, now let us try to find out the solution for the first equation, okay, that is with corresponding to 0 at the right hand side over here. So, again it is a natural response. So, its solution is going to be this one. And for the force response we can assume say a step input say at t is equal to 0 with a step size of k. If I do that basically this is what is my equation. As I said I can assume some solution for that, say v is equal to b, which is a constant. If I substitute it over here, this term will become 0 because I am taking b as a constant. So, a0b is basically b0 into k, where k is the input of a step size input of a step size k over here. Okay. So, from here I get the value of b, so I get the solution. So, I can write the complete solution like this. Okay. So, this is the case for the solution of first order differential equation with a forcing function. Okay. So, again I can get the value of a by substituting say at t is equal to 0, x is equal to 0. So, if I put it over here, okay, I can get the value of a as this one, I can substitute it over here. Okay. So, this is my the final response. So, this is my step input which I said in my first order differential equation with a forcing function. So, this is my response basically. So, here as you can see that if I take the value of t is equal to infinity basically. So, this value is going to be 0. So, I will be getting this value. Okay. So, this is what I am getting at t is equal to infinity b0 by a0 into k. Okay. So, this is the resulting response. The previous example which I have shown that was case of a tank on which water is filled up. Okay. We can have another example of the first order system with a forcing function is that of a DC motor. Okay. So, in case of DC motor, as we have seen in modeling of electrical systems, we have this as the these are the equations. Basically this is the equation for the armature control motor, where this is basically the voltage supplied to the armature, and this is the back EMF basically, and so and these are the voltage across the impedance sorry inductance, and this is across the resistance, and this is equation for the load actually. Okay. So, here we can simplify these equations, that is substitute for IA from the first one and second one. So, this is what I can get. Okay. So, this is also a first order differential equation of this form, similar to what we have seen as the water being filled up in a tank. Okay. So, here you can see that output is omega and input is the voltage supplied to the armature. Okay. So, we can have the treatment similar way. Now, if I look at this expression for the solution for the differential equation with a forcing function, that is the first order differential equation. This is my expression, and we have seen that this is the steady state value. Okay. So, this is a steady state value into this part. Now, here you see that if I write t is equal to a0 by a1 basically sorry a1 by a0, then these terms will be getting cancelled, and we will have that is value of x. Okay, and that will be actually 0.63 times the steady state value. Okay, and this time is basically called the time constant. Okay. So, this is a1 by a0, that is known as the time constant, and if I write it in terms of that, then this is my response of the first order system for the step input. So, at tau is equal to 1 or 1 tau, this is 0.63 basically. So, fraction of steady state value if I plot over time. So, this is 0.63 at 1 tau, and this way I can have basically the response. So, you can see that at time infinity I get the steady state value, that is 1 over here. Next, let us talk about the second order system. Okay. So, second order system, as we have seen that they have d square by x by dt square type of terms are there, and second order system can consist of say inertia, compliance and damping for a mechanical system, and we have also seen at several occasions during this course the electrical system can have the resistor, inductor as well as the capacitor. They also represent the second order system. Okay. So, let us take the second order system, a simple spring mass damper system over here. Okay. So, this spring mass damper system is excited by say an external force F. Okay. So, in this case my input is a F and the output is basically this displacement x over here. So, I can write the equation of motion for this system by drawing the free body diagram, and it is this basically m d square x by dt square plus c dx by dt plus k x is equal to F. Okay. Yeah. So, the variation of x with time depends on the amount of damping present in the system, and the force is applied say as an step input. Then if there is no damping present in the system, then mass will keep on oscillating, and the damping basically that causes the oscillations to die away until unless the steady displacement of the mass is obtained. Okay. And if damping is high, then there will not be oscillations, and which means that the displacement of mass will slowly increase with time and moves towards the steady displacement position. Now, first let us consider the second order differential equation with no damping. Okay. So, if there is no damping and there is no input excitation, so I take here 0 and I have input force 0, and I can take this C also 0. So, we will have because damping is not there, so we will have the continuous oscillations, and we can assume the solution of say this form A sin omega n t. Okay. So, my solution is A sin omega n t if I take first derivative. So, this A omega n cos omega n t, and if I take second derivative, then this is minus A omega n square sin omega n t. Now, you see this is A sin omega n t is same as that of x. Okay. So, I can write this as minus omega n square x, or I can write it in this form. Now, if I compare this equation with the equation without damping, okay, that is this one, okay, then you can see that omega n square corresponds to k by m over here. So, omega n square is equal to k by m, okay, or I can write the solution as A sin under root k by m t, and this is the solution of differential equation if there is no damping. Okay. Now, what if there is damping? Okay. So, if damping is present, then this term is not going to be equal to 0, and we have say the excitation force also F being over here. So, again here I can take the solution of to be composed of two forms, that is the natural response and the force response, and as we have done earlier we can substitute this solution in this expression, and we can segregate basically the two parts over here. Okay. So, this part we can equate to 0, which will be giving the natural response, and this part will be going to equal to this one, and that will be giving us the force response. Okay. So, if we look at solution for the transient equation, okay, that is for the natural response. So, here I have I can take x n is a e to the power s t as the solution, and if I substitute it back over here, okay, so I get this one, and this cannot be equal to 0, as because if I make it is equal to 0, this itself will become 0. So, I make the other equal to 0. So, this is my auxiliary equation. So, from here I can get the value of S. It is a quadratic equation. So, its solution is going to be this form. Okay. And if I define this omega n square is equal to Km, as we have seen for the natural response, and say I define zeta square as this one, then zeta is going to be equal to this one. Okay. So, I can substitute that over here and I can get the root of this form. Okay. Now, here there are 3 cases we are going to have. This zeta, if it is going to be more than 1, then these are the 2 solutions which I am going to get, S1 and S2. So, the general solution is going to be this one. Okay. And we will say that the system is over damped. And if the roots are equal, then naturally this is going to be the solution. This is going to be the root, these are going to be the roots both equal, and this is going to be the solution, and the system is said to be critically damped. And if this is less than 0, then the 2 roots are complex are going to be there. Okay. We define this as the damped frequency. Okay. And the 2 roots can be represented like this. So, this is going to be my general solution. Okay. If I just substitute, I can further simplify this solution, okay, by representing the exponential function as cosine and sine functions. Okay. And this is going to be my natural response in that particular case. Okay. So, this is the natural response, and this one is called damped frequency of oscillation, as I have explained to you. Now, solution for the forcing equation, if we look at this one. So, as we have seen for a step of size f at time t is equal to 0, we can take solution, say x f is equal to a constant. Okay. So, k a is basically f. Okay. So, my a is f by k. So, the complete x f I can get from here. Okay, that is x f is equal to a. So, it is f by k. So, my complete solution I can write for all the 3 cases, that is for zeta greater than 1, I add it up here, over damped case, for critical damped case I add it up here, and for the under damped case I edit it over here. Okay. So, when t is tending to infinity, above equation leads to actually x is equal to f by k, which is the steady state solution over here. Okay. So, here you can see that this is the over damped case, critically damped case, and this is the under damped case, and this is my f by k, the steady state solution. Okay. Another example, as I was telling you, in electrical system, it is a simple RLC circuit, which is an example of the second order system. We can for a given step input, I can write the Kirchhoff's voltage law basically. Okay. That is KVL, and I can write this voltage across resistor, inductor, capacitor, okay, and IR, and this L di by dt plus Vc, I can write it like this. So, this way I can write the expression like this one. Okay. Then there are various performance measures parameter, and these parameters are how the systems is responding. Those parameters can be measured with the help of, say, delay time, rise time, peak time, maximum overshoot, and settling time. So, with the help of these parameter, we can measure the performance of the dynamic system. So, what is the delay time basically? So, if I plot x versus omega t over here, so it is the time required for response to reach half of the final value at very first time. So, say this is my steady state value, that is the final value. So, 0.5 of xs it reaches over here. So, this time is what I am calling as the delay time. okay, and the rise time is the time taken for the response to rise from say 0 to the steady state value. Okay. So, this is steady state value. So, this time is actually my rise time, okay, that is moving from here to here, whatever time is taking, that is the rise time, and it is a measure of how fast a system responds to the input. It is the time for oscillatory response to complete a quarter of a cycle. So, this is omega T r is equal to pi by 2. Okay. So, this way we can find out the rise time, and for overdamped system T r is considered as the value for the rise of response from some percentage of steady state value. So, say 10% to another specified percentage, say 90%. Then another parameter is the peak time, okay, and it is the time taken for the response to rise from 0 to the first peak value. So, here you can see that the first peak value is coming over here. So, it is actually this time, this is your peak time basically, okay, and it is the time of the oscillation response to complete one half of the cycle. So, this is how it is written as pi over here. Okay. Then you have the maximum overshoot. Okay. So, this is actually from the steady state value, whatever value response, how much is the maximum value from the steady state, that is what is called as the overshoot. Okay. So, it is the maximum amount by which the response exceeds the steady state value, and it is amplified amplitude of the first peak basically, and this overshoot is written as percentage of the steady state value, okay, and maximum percentage overshoot directly indicates the relative stability of the system. And this maximum overshoot can be derived to be like this in terms of the steady state value, and in terms of the maximum percentage overshoot it could be derived like this. Okay. I am not working on the derivations over here, you can refer the reference books which I will be telling you towards the end of this lecture. So, percentage of the peak overshoot, it is going to be, as you can say, a function of the damping ratio over here. Okay. So, say for damping ratio 0.2 overshoot is 52.7 and so on. So, as you can see, as we are increasing the damping ratio, the overshoot is decreasing basically. Okay. So, that is one of the observation which I wanted you to observe. Then the subsidence ratio or the decrement, it is again another performance measure parameter, okay, and this provides the information about how fast the oscillations are decaying, okay, and it is defined as the ratio of the second overshoot to the first overshoot. Okay. So, first overshoot occurs at say omega t is equal to pi, the second overshoot will be occurring at omega t is equal to 2 pi. Okay. So, the first overshoot can be written like this expression, the second overshoot expression can be written like this. So, the decrement expression can be derived in this way. Then the settling time actually you see that for a system reaching of the exact steady state value may not be possible. Okay. So, when do we say that the system has reached the steady state value? Okay. So, there is a certain percentage of the steady state value, say 2%, if your system reaches say 2% of the steady state value, okay, within that limit if it is there, we say that the system has got settled basically. Okay. So, the settling time, this Ts for the basically you can see that this zone is actually 2% of the axis. Okay. So, wherever this has been achieved, that time is called as the settling time, okay, and it is measured by the time taken by the response to fall and remain within some specified percentage of the steady state value, and this for the 2% of the settling of axis, this value can be worked out as 4 by zeta omega n. And then another performance parameter is the number of oscillations, and this is given by the settling time divided by the periodic time. So, settling time of 2% settling time divided by periodic time, if I substitute it over here, okay, this is how get the expression for the number of oscillations, which is again function of the damping ratio. Okay. So, these are the further references you can look at if you want to read it further. Thank you very much.